Hi everyone, my name is Ryka Chopra and I'm a part of YouthSTEM organization. And now we're going to be looking at part two of my combinatorics lesson, which is counting. So in part one, we looked at probability, which, as just a very brief recap, is basically how you can find the number of favored outcomes over the number of total outcomes. And today we're going to be looking at counting. And there are a lot of different things I want to go into in counting, so let's jump right in. So first of all, what is counting? So a very basic definition of counting is about the number of ways of choosing some objects out of a collection or an arrangement. So there are a few things that you must know before you can actually get into counting. So I will quickly go over that. So first thing is you need to know what factorials are. And this is really easy. If you don't know what factorials are, then I assure you it's extremely easy to learn. So, an factorial is represented by an exclamation mark. So in math, if you ever see an exclamation mark, the problem writer probably isn't super enthusiastic about a number. They're just trying to signal that it's a factorial. So if you have a number n, an n factorial is just n times n minus 1 times n minus 2 all the way up till 1. So it's just the product of all the numbers from 1 to n. So for example, 4 factorial is 4 times 3 times 2 times 1, which is 24. 3 factorial is 3 times 2 times 1, 6. So very easy. And second thing that you need to know is what a permutation is. So a permutation is kind of like all the arrangements for a certain set of objects in a way. So what a permutation is, and one thing that I want you to keep in mind is what the formula I'm about to show you only works when all of the numbers are different. If or all of the numbers or all of the objects are different. And if you have repeats or if you have like multiple of something, like if you have the numbers 1, 1, 3, 5, there's an additional part. So this is only if everything is distinct. So if you have, let's say, the numbers 1, 2, 3, you want to find the number of arrangements for these numbers. That is the number of permutations. So 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. These are all the permutations of the set 1, 2, 3. So these are all the different arrangements, and as you can see, there are 6 arrangements. So in general, to find the number of permutations of objects, like if you have an apple, banana, and let's say orange, and you want to find the number of ways you can sort these three, this is the exact same thing as the 1, 2, 3 case. It's just instead of numbers, they're objects. This, you can find this by a simple formula, which is the number of objects, factorial. That is how you find the permutations when all of the numbers are distinct. So if you had 2 apples, banana, and orange, you would have a different step, but we will not go into that right now because there is a few other things I wanted to mention before we jump into that. So now I want to tell you about combinations. And you might think, are combinations and permutations the same thing? Well, no. When you have combinations, so when you have permutations, the order matters. So, here, I'll give you an example. So if you're like, let's say 1, 2, these two numbers, right? Actually, it might be easier for you to understand if we have different people instead. So let's say you have 2 people, Alice and Bob, right? You have Alice and Bob. And Alice and Bob and Alice, when you take into account permutations, these are different. These are distinguishable. Even though it's the same people, they're in a different order. That's what distinguishes a permutation from a combination. In a combination, as long as the people or the objects or the numbers are the same, the order does not matter. So the number of combinations is one. There's like one way you can choose both Alice and Bob, but the number of permutations, so how many ways can you order Alice and Bob, is two. And that's another thing that is something I want to bring your attention to. So when you're thinking of permutations, think how many ways can I order this? When you think of combinations, think how many ways can I choose a certain number from this set. So what I'm going to do is I'm going to show you a different way of thinking about this. So let's say now Alice and Bob invite a friend, Claire. Okay, so now you have Alice, Bob, and Claire. And let's say there is going to be a project, and then two of them are going to be partners. So we're going to choose two out of these three people. So what can it be? I'll just call them A, B, C for short. So A, B, C. You can have Alice and Bob be a pair. You can have Alice and Claire be a pair. Or you can have Bob and Claire be a pair. Now, is Bob and Claire any different from Claire and Bob? No, they're the same. Because again, we don't care about their order. We only care about the people. So this is the CB is the exact same as BC. So we don't care about that. So in total, there are three combinations, three ways of choosing two out of the three people. Okay, so let's just generalize this and have a formula. So our formula for this, so let's say we want to choose, I'll write it like this. Are objects out of a collection of n objects. So for example, in this case, we had two people out of a collection of three. This is n choose r. Now, what does this mean? This is equal to n factorial over n minus r factorial times r factorial. Okay, so what is that? So that is, so in this case, we have 3 choose 2. So 3 choose 2 is 3 times 2 times 1 over n minus r factorial is 1 factorial, and then r factorial is 2 times 1. 2 times 1. This cancels out and it becomes 3. Let's look at a different example just to kind of look at this new function I showed you, the choose function. So let's do this in a different color. Let's do this in red. So let's say you want to calculate 7 choose 3. So on top we have 7 times 6 times 5 times 4 times 3 times 2 times 1. On the bottom, n minus r is 7 minus 3, 4 times 3 times 2 times 1, and then r factorial times 3 times 2 times 1. So this cancels out, and then we are left with 7 times 6 times 5 over 3 times 2 times 1. So that leaves you with, you can cancel these out, 35. So 7 choose 3 is 35. So being able to calculate these is an important part of combinatorics. And that is kind of the main difference between permutations and combinations, which are two of the main branches of counting. And what I want to kind of end this video with is the different forms of counting which you might encounter. So let's get rid of all of this. And actually, I'll just clear everything. So now what I want to tell you about is casework. Oop, let me change the color. Casework counting and complementary counting. Complementary, long word. So casework counting and complementary counting are two of the main kinds of ways that you can count anything really. So for casework, it's on a case by case basis. So, for example, uh, let me give you a very kind of brief overview of what it is. So casework counting is basically it's where you split a problem into smaller subproblems in a way. And casework is basically like brute force. So if you have a chance to do complementary counting and you think it'll be less time consuming, then I would recommend you look at the complementary counting option first and then leave casework as a last resort. But of course, it is a good method to know. So one example of casework counting is, let's say, how many words are less than 4 letters long and only contain the letters A, B, C, D, E. So we want how many words can you form? So less than 4 letters, and it contains A, B, C, D, E. So a word is like any string of these letters. So now what we can do is we can split this problem up into cases, and we can do this based on the length of the word. So let's say you have case 1, which is it's 1 letter long. 1 letter. And here there are only 5 options, which is just A, B, C, D, or E. And let's say case 2, there are 2 letters in the word. Then this is just 5 times 5 because you have 5 options for the first letter and you have 5 options for the second letter. So 25. And again, if you remember from my previous video, you have the word and here. So even if it's not probability, you're still going to multiply because it's and. And then you have case 3, the last case, which is 3 letters. And then again, it's 5 times 5 times 5, which is 125. So to find the total final answer, you can just take the sum of all of these because our total number is just going to be all of these subcases combined, which ends up being 155. Okay, so that is a very kind of basic example of what casework counting is. And now we're going to look at what complementary counting is. So complementary counting is a very useful technique, and what it is basically if the question is asking, for example, how many A's are not in B, or like how many cases are there where this does not happen, you're going to find the cases where it does happen, and then you're going to subtract it from the total number of cases. So I'll give you an example, or actually I'll write it in probability terms first. So as we learned in the previous lesson, P of A refers to the probability that A happens. So P of A is going to be 1 minus P of not A. So so A is complement basically. So the probability that something happens is 1 minus the probability that it does not happen. And here's an example. So let's say how many positive integers less than 100. So positive integers less than 100 are not multiples of 5. Multiple of 5. So first, how many total numbers do we have? We have 1 through 99. So this is 99 numbers. And now we want to find the opposite of what the question is asking for. So we want to find the number of positive integers less than 100 that are not multiples of 5. So let's find the ones that are multiples of 5 and then subtract that from the total. Mults of 5 are 5, 10, 15, all the way up till 95. So this is 19 numbers. So now to find what the question was asking for, which is not the multiples of 5, we are going to subtract 19 from 99. So not mult is going to be 99 minus 19, which is 80. And that's our final answer. So those are the two basic kind of steps there are to counting. There's casework counting and complementary counting. Again, I believe complementary counting is more efficient, but you cannot use it in some cases. And casework will always work, but it can become very bashy and complicated, so just keep that in mind. That concludes our combinatorics series. So I hope you enjoyed the lessons and I hope you learned from them. Thank you so much.